Hello, thanks for joining me. This is going to be a review of 1.10, and it's actually 1.09 as well. We're going to factor completely and graph. We're talking about polynomial functions, equations, graphing them on the coordinate plane, and we are putting a bunch of things we've learned together. So kind of pay attention as we go along. You'll see us doing different things. For example, we will be using synthetic division both for factoring and for graphing. So finding the points to plot and also finding those roots. There it is, roots. We're going to factor roots, graph, and then we'll describe the graph and what it looks like. And we'll also use some other tools that we've learned for helping us along the way. Okay, we're only going to do one problem in this recording. My intention is to have a second recording that basically does the same thing, so you can see more than one example. So here's our function. I didn't even put it in function form. I probably should have said f of x equals here, so we can do that if you want. But this is our function, and the first thing that we're going to do is we're going to factor it. Now, as I factor, I wanted to just real quickly make the connection between the factors and the roots. So remember that when we have a graph of a function, and this is not the graph of this function, we have the points where the graph crosses the x-axis. We call those the roots. And if there's two of them, then it's a function, x squared function. And the roots, we'll call them root 1 and root 2, relate to the factors of the equation that gave us this graph. In this way, the factors are x minus root 1 and times x minus root 2. So the roots are the numbers that we subtract from x. If they're negative, we end up adding them in the factors. So the factors and the roots relate to each other, and that the numbers you see in the factors are the opposite of the numbers in the roots. And in fact, we're going to see this eventually. When you're solving by factoring, remember you're going to take x minus whatever that number is equals 0, and so if x minus r1 equals 0, then x equals, add r1 to both sides, r1, and so that's the root, and because the factor equals 0, then x equals the root. Okay, so that's kind of the relationship between the graph and the factors. So as we go through here and factor this polynomial, we're going to be picking up some vital information that we'll use when we graph. Okay, so hopefully this will all make sense as we go along, but I wanted to start off with that. Okay, so how do we start? We're going to factor, and we're going to factor, back in the day we used to factor, we use lots of different methods for factoring, but at this point, with a fifth power polynomial expression, the only thing that we can do is synthetic division. And I'm going to use the method of synthetic division that allows me to do a bunch of factoring at once, or a bunch of synthetic divisions at once. So I'm going to put it in this format, and I put my coefficients on the top bar, so the 1 for x to the fifth, x to the fourth, the coefficient is -2, x to the third, -4, x squared is +4, x to the first power is -5, and x to the 0 power is that 6. And then this column here is where we're going to have our remainders, if they're, our remainders, whatever the remainder is, could be 0. Okay, now we're going to do synthetic division, and remember that we had a little trick for helping us to know what the rational roots are, and that the rational root, I think it was the rational root theorem, where we take the last coefficient and make that its factors the numerators, and the first coefficient in this case is 1, and make that its factors the denominators, and we just kind of mix them up. So all the factors of 6, both positive and negative, matched up with all the factors of that 1. In this case, it's going to be pretty easy because it's a 1. If it was a bigger number, then there would be some fraction answers here. But take all those, put them together, and the potential rational roots. And remember, this is just the possible, so we say possible or potential, will be all those different combinations of numbers. So factors of 6 are 1 and -1, so plus or minus 1 over 1. 2 and -2, so plus or minus 2 over 2, plus or minus 3 is a factor of 6 over 1. I said over 2, I meant over 1. And then plus or minus 6 over 1. So I have 2, 4, 6, 8 possible rational roots. So that's where I'm going to start. I'm going to start with those and see which of those is going to be are going to be the roots for this, or are going to give me my factors. All right, so let's just start with the easy one. We'll start with 1 because it's easy. And remember, we bring down the first number on top, 1, then we multiply by what we're doing the synthetic division with, 1 times the 1, and then we add that to the next number. -2 plus 1 is -1. Do it all over again. We do the 1 times the -1, and that's -1. Add it to the -4, that's -5. Okay, so this is synthetic division doing what would normally be 2 steps. Multiply by the number here, the 1, and then we normally would write it down, and then we add it to the number up on top, so that we're doing both those steps at once. So 1 times -5 is -5, plus 4 is -1. 1 times -1 is -1, minus 5 is -6. And 1 times -6 is -6, plus 6 is 0. And so right off the bat, we hit it. We got one of our roots. So that means that on our graph, there is a point where x equals 1 and y equals 0. Of course, that point is on the x-axis. That's why this is called the root. It's where the graph hits the x-axis, or one of the places. And that means that x equals 1 is a root, and x minus 1, you see the connection there. If x equals 1 is a root, then x minus that number, x minus 1, is a factor. Okay, so there we have basically 2 pieces of information. We know that there's a point 1, 0 on the graph, and there's a factor, x minus 1 is one of the factors. And we're looking for the factors now, and we're going to set our roots, our ordered pairs, to the side and use those later when we graph. Okay, let's do it again. We tried 1, let's try -1. So bring down, oh, and notice this. This is the cool thing. If we're using this format for doing synthetic division, we can cross off that first row. We're oh, I'm sorry. Nope. Take that back. That was false. Okay. I was wrong. Okay, this is the really cool thing. We did our synthetic division. We came up with a remainder of 0. That means that these numbers here, the numbers over here that are down here, these numbers are roots. Like, I'm sorry, are part of another polynomial, a different polynomial that is a factor of this one, right? If we divide this by x minus 1, we get a new polynomial that's x to the 4th minus x to the 3rd power minus 5x squared, and so on and so forth. So since we're just trying to find all the factors, we divide out one factor at a time, and then we take what's left over and try to find the factors that remain in that part. So what the answer was. So since the remainder is 0, this is a factor, and now we're going to take the answer and we're going to try to find the factors in that. So these are our new coefficients that we're going to use. We don't have to put x's back in there. We just use these as they are, and we use them where they're at. And so to kind of help us remind ourselves that that's what we're doing, we're going to cross off this top line. We're not going to use those coefficients anymore, and instead we're going to draw a line under here and do synthetic division now in that spot. So bring down the 1 times -1 is -1 plus -1 is -2 times -1 is 2 plus 5 is -3. -5 is -3 times -1 is 3 minus 1 is 2 times -1 is -2 minus 6 is -8. Okay, now that one did not work. The remainder, this is the new remainder column, the remainder is -8. And so that's -1 is not a factor. We're going to cross that line off, and instead of rewriting all this, we're going to just try to keep in mind that we're continuing to use this line of coefficients for synthetic division, and we're just going to ignore the line under it and just go to the next line. So we tried 1, we tried -1, let's try 2. So bring down the 1 times 2 is 2 minus 1 is 1 times 2 is 2 minus 5 is -3 times 2 is -6 minus 1 is -7. I'm doing that right. Okay, times 2 is -14 minus 6 is -20. So that one didn't work at all. So 2 is not a root. X minus 2 is not a factor. So we cross that one off. And now we try the next number in our list of possible rational roots. We tried 1, -1, 2. Now we're on to -2. So again, continuing to use that 1, -1, -5, -1, -6. Bring down the 1 times -2 is -2 minus 1 is -3 times -2 is +6 minus 5 is 1 times -2 is -2 minus 1 is -3 times -2 is +6. +6 minus 6 is 0. Whew, finally we got a remainder of 0, and since we have a remainder of 0, that means that the -2 that we used in our synthetic division is a root. So there is a point -2, 0 on our graph, and one of our factors is x minus -2. So x minus -2 is +2. Now notice what's happened. Now we have a whole new set of numbers, the coefficients that we're going to use. We're going to stop using these 5 numbers up here, and we're going to start using these 4 numbers that are left over. This represents x to the 3rd power minus 3x squared minus or plus x minus 3. Okay, so that's an x to the 3rd power polynomial, right? We've divided out 2 factors of x, binomial factors, x minus 1 and x plus 2, and what's left over is an x cubed polynomial, and we're going to divide further and try to get it down to an x squared, a quadratic, and then we'll use the quadratic formula to get the rest. Okay, so we're going to keep going, but notice that now the last number here, remember we came up with our possible rational roots based on this +6. Now the last number is -3. So we know that the plus or minus 6 is not going to work anymore for sure. I mean, it never was going to work, but now we know that for sure because it's not a factor of the last coefficient here. So we're kind of running out of things to try, but we haven't done the 3 or the -3, so let's do those. Let's do 3, and we're going to draw a line under here. We'll draw a line through here just to remind ourselves we're no longer using that set. And we'll do 3. So bring down the 1 times 3 is 3 plus -3 is 0 times 3 is 0 plus 1 is 1 times 3 is 3 minus 3 is 0. And there it is, my last remainder of 0. And so I am very happy. We have another point on the coordinate plane, 3, when x equals 3, y equals 0. Again, that's another point that is on the x-axis, so that's a root. And we can also say that another one of the factors is x minus that value 3. All right, so we have 3 factors. And then what we have left over, and I'm going to go ahead and write it down here, is 1x squared plus 0x plus 1. And we can, instead of continuing with synthetic division, and we're really out of options, we could try x equals negative 3, but we know that's not going to work. Well, okay, let me be really careful about that. We tried all of our possible rational roots once, so we tried 1, negative 1, 2, negative 2, 3, negative 3. Well, we didn't try negative 3. We know it's not going to work. But we have to be careful that anytime we had a success, remember x equals 1 was a success, we should try that number again because of the possibility of a double root having the same root twice. So I haven't tried 1 twice, and I could if I wanted to, and I haven't tried negative 2 twice. I could if I wanted to. But when we get down to 3 terms here, and this is really important, this is a lot of people have trouble with this. When we get down to 3 terms here, 3 numbers, after not including the remainder, then we don't have to do this method anymore. And let's admit that this method, this synthetic division to try to find the roots, is a guess and check method. Sometimes we hit it, and sometimes we don't, and sometimes it takes a while to get the roots. So this is a guess and check method. That means it's not the most efficient way to go. We like it better if in math we could actually use a formula that will get us the right answer every single time without having to guess. And that's what we can do when we get down to a quadratic. When we get down to a quadratic, when we have the highest exponent is 2, x squared plus 0x plus 1, we can use the quadratic formula. And the quadratic formula goes like this. If you have x squared plus 0x plus 1, oh my goodness, let me just rewrite that. Let me say it again. If you have ax squared plus bx plus c equals 0, and that's what we're doing here. We could have said the whole thing equals 0. That would have been more proper. Then, if you have that, then x equals, here it is, negative b plus or minus the square root of b squared minus 4ac over 2a. That is called the quadratic formula. It's very powerful. It does require that you start off with an equation in this form. It's a quadratic that has an x squared. And then you identify the 3 coefficients, a, b, and c, and you plug those into that formula where the a's and the b's and the c's are, and we'll get our answers. And it's always going to be 2 answers. That's why we have a plus or minus. We do it once with the plus, and then we do it once with the minus. And that always gives us our last 2 roots, our last 2 factors. Okay, now I'm showing you all that to remind you that the quadratic formula exists, and that it's okay to use it, or it's proper to use it in this context. But we didn't need to write all that stuff. All we needed to know is we have 3 numbers here at the end. It's their last 3. And so we say the first one is a, the second one is b, and the third one is c, and we plug those into the quadratic formula. So I get x is equal to, here's the quadratic formula, negative b, so negative 0, plus or minus the square root of 0 minus 4 times a times c, a and c are both 1, over 2 times a. Now multiplication, 4 times 1 times 1 is 4, so 0 minus 4 is negative 4. And of course negative 0 is just 0, so it's plus or minus 0 plus or minus the square root of negative 4, and then over 2 times 1 is 2. The square root of negative 4 is, we do imaginary numbers here, plus or minus 2i over 2, divide that by 2, 2 divided by 2 is 1. So my answer then is x equals positive or negative I, that's an imaginary number. And so my last two factors are x minus I and x minus negative I, so x plus I. So there's my 5 factors. Let's talk a little bit about imaginary numbers and what do they mean on the when we talk about graphs. So I'm going to go to the next page. We have our 3 points for our graph, and we could put those in at any time. 1, -2, and 3 are the roots. But then we had two other factors. Remember that if we have x to the 5th power, we need to have 5 factors, so 5 little binomial x minus somethings. And we have that, but 2 of them don't correspond to any number on the x-axis, to any real number. So let's talk about what that means on the next slide for just a minute. So you know that if you have x to the 5th power, it's a positive number in front of x, is positive x to the 5th power, that the left side of the graph is going to go down, the right side of the graph is going to go up, and then the 5th power means that it's going to go up for a while, and then it's going to go down for a while, and then up, and then down, and then up one last time, and there we have it. Now, if we have our coordinate plane here, let's just draw the y-axis. If the x-axis was here, then there would be a potential where we hit the x-axis 1, 2, 3, 4, 5. We would have 5 roots that correspond to 5 the 5 factors. X minus each of those numbers would be a factor. But that's not the only way that this can be configured. So just imagine that instead of the x-axis being there, what if the x-axis was just a little bit lower, so that we cross the x-axis once there, and once there, but this last time when it turns the corner comes down and goes toward the x-axis again, and it should potentially go across the x-axis, doesn't quite make it. It turns the corner and goes back up again. Okay, that is an indication. That's what it means when we have imaginary roots. X equals I and x equals negative I. Imaginary roots are an indication that the math here is trying to explain where the graph crosses the x-axis on this occasion, but it doesn't cross the x-axis on this occasion. So the math is not able to tell us there isn't any roots it doesn't cross. Instead, it has to come up with, we had to say, well, there's 2 imaginary roots because we imagine it could have gone across the x-axis, but it just didn't. And there's 2, should have hit the x-axis 2 more times, but it just happened to not do that. And so that's what the imaginary roots are telling us. Okay, I wanted to explain that before we get into the true graphing here. Before we really before we can actually get out the graph paper, which we'll do on the next slide, we need to have a few more points. Remember that we had the roots at -2, 1, and 3. So we know those, but we need to find some other points, and to find points on the graph, we can do synthetic division. So wouldn't you know it, we're just going to spend the entire day doing synthetic division on this problem. We're going to start with the coefficients again, -2, -4. Am I doing the same problem? Yeah, okay. I lost track of what my numbers were. 4, -5, oops, and 6. Okay, now this time we're going to use these coefficients the entire time. Remember, once we found the first factor, the first root, we had a remainder of 0, we stopped using these numbers and moved on to the next row. Well, now we're going to keep using these ones over and over again, and our goal is to get remainders here in this last column, and those remainders are going to be the y values when the x value is the number that we do our synthetic division with over here. Okay, so x values are going to be inputted here. We're doing synthetic division. This is the remainder theorem. The remainder is the y value on the coordinate plane for that x value on our graph. So that's going to make this really useful. So we're going to not use any of the numbers that we've already discovered are roots. Let's remind ourselves what those are. So 1, 3, and -2. So I'm going to write those down. So 3, 0, 1, 0, and -2, 0 are already points that we know. And then there's another point that we know. It's the y-intercept. When x equals 0, what does y equal? I hope you know, or I hope you can see from this equation that if you took all those x's and made them zeros, all the first 5 terms would go away, and we'd be left with that number without an x, which is the 6. So we have a fourth point there on top of the roots. That is the y-intercept at 0, 6. We don't have to do any calculation there. It's just, you can tell just by looking. Okay, so then we're just going to plug in the other numbers kind of around these x values and see what we get. So we don't have 3, x equals, I'm sorry, -3. We don't have x equals -3. We don't have x equals -1. We have x equals 0, 1. We don't have x equals 2. And we might try x equals 4. Okay, so we're going to do synthetic division just to kind of fill in the gaps, put some other points on the graph besides those 4, which mostly are x-intercepts. Okay, so we bring down the -2, and we multiply it by the -3. -2 times -3 is 6, minus the 4 is 2, times -3 is -6, plus the 4 is -2, times -3 is positive 6, minus 5 is 1, times -3 is -3, plus the 6 is 3. I think I did that right. Yep, looks good to me. All right, so that tells us that we have a point on our coordinate plane, and we'll use this, -3, 3. So we'll definitely want to put that one in. Oh my goodness. I knew I was missing something here. You guys didn't stop me. Okay, hopefully this is okay. Were you screaming at the computer screen here? I knew this wasn't right. I couldn't figure out why. Okay, what did I miss? I missed my first coefficient. I missed the coefficient of x to the 5th power, which is the 1, and that's going to make a huge difference, isn't it? So let's do this all over again. 1, -2, -4, 4, -5, and 6. Okay. That was a close one. Just about completely messed this up. Okay, let's try it again. Can I pause and just meditate on my mistakes here? Recognize that this is really complex stuff you're doing. You should expect to have to make mistakes like I did, and you're going to need to learn to catch your mistakes. That's part of learning to do really complex math, is just learning to just double check things and ask yourself, does that make sense, and does it fit into the graph? The reason I knew that -3 was not quite right is because I knew that the left side of the graph goes down forever, and -3 is the farthest left point I have, and if it's above the x-axis, then that means there's another root over there somewhere that's that I didn't find, and that's not possible. So there was something that just didn't seem right, and so I checked it, and then I found my mistake, and now I've kind of crinkled up my paper, thrown it away, and got out a brand new fresh sheet of paper, and I'm going to try over again. All right, so we're going to bring down the 1, and so this math takes lots of paper, takes lots of scrap paper, lots of balls of paper crinkled up, thrown at the trash can. That's just part of doing this tough math. All right, bring down the 1 times negative 3 is negative 3, minus 2 is negative 5, times negative 3 is positive 15, minus 4 is 11, times 3 is negative 3 is negative 33, plus 4 is negative 29. Now, at this point, you can see that's getting pretty big, and when I multiply it by negative 3 again, it's going to be really big. Negative 3 times negative 29 is negative 87, I think. Or positive 87. Sorry, it's going to be a big positive number, but then we're going to multiply it again, and it's going to be really negative. Okay, so positive 87 minus 5 is 82. And then times negative 3. Now, I'm just going to do a little math trick here. Negative 3 times 82 is a really big negative number. It's like in the hundreds. So I'm not even going, it's a big negative number. When I add 6 to it, it's still going to be a big negative number. Didn't change that much. So I'm just going to write that. Now, if you want to, get your calculator out. But we're not going to graph the point negative 3, negative whatever that is, 160 something. I think it's 166. Negative 3. I'll just go ahead and write that down just to make us feel better. Negative 166. We're not going to have a piece of graph paper that goes all the way down to negative 166. We're just not. So we'll kind of figure out a way to make that graph look right when we come to that point. But just understand that that kind of verifies for us that the left side of the graph is going down, way down, right away very fast. So as x gets bigger, further and further away from 0 in the negative direction, as it heads towards infinity, it doesn't have to go toward infinity very long. It just, in negative 3 is enough for it to just shoot down really far. And it's going to keep doing that. Okay, so next one. At x equals negative 2, we know that y equals 0, so that line goes up, hits the x-axis, and so then we want to see where does it go after that. So we're going to plug in x equals negative 1. Cross off this line. We're done with that. So bring down the 1. Negative 1 times 1 is negative 1, minus 2 is negative 3, times negative 1 is 3, minus 4 is negative 1, times negative 1 is 1, plus 4 is 5, times negative 1 is negative 5, minus 5 is negative 10, times negative 1 is 10, plus 6 is 16. So here we go. That's kind of what we expected. When x equals negative 1, y equals a positive number, and it's not too far off the chart. We could probably graph that. Okay, now we know that after negative 1, when x equals 0, y equals 6, so it turns the corner at some point and goes back down to 6, and then at 1, when x equals 1, y equals 0, so it goes across the x-axis. So when x equals 2, we want to know what happens. Bring down the 1, cross that off, times 2 is 2, minus 2 is 0, times 2 is 0, minus 4 is negative 4, times 2 is negative 8, plus 4 is negative 4, times 2 is negative 8, minus 5 is negative 13, times 2 is negative 26, plus 6 is negative 20. So that one's pretty far down there at x equals 2, y equals negative 20. But we know when x equals 3, it goes back up to, goes back up to 0. So it's going to go down to negative 20, but then it's going to turn around and come back up to 0 when x equals 3. And where's it going to go when x equals 4? So we'll do that. Bring down the 1 times 4 is 4, minus 2 is 2, times 4 is 8, minus 4 is 4, times 4 is 16, plus 4 is 20, times 4 is 80, minus 5 is 75, times 4 is 300, plus 6 is 306. And so you can see when x equals 4, y is way off the chart, 306. Okay, now we're going to take these points and we're going to graph them. And as I'm looking at these, obviously I'm not going to be able to graph -3, -166. I'm not going to be able to get a piece of graph paper that will cover that. But I can kind of note that that is the direction the line is going. As it gets toward -3, it's going to go down very far. And then same thing with the positive for 306. It's going to be way too far off the graph. Not going to be able to graph that. But I can note that and note that the graph is going in the positive direction. Okay, I'm going to go to the next page. I have some graph paper here. I'm going to create a coordinate plane very carefully. I can't get the 306 and the -166, but I'd like to get that all the way down to -20 and all the way up to +16. So I'm going to draw my coordinate plane like this. A little bit more space down below than up above because we have a y value that's a negative y value that's further away than the highest positive y value. I'm going to draw my x-axis right in the middle, so I've got points on each side. And then I'm going to start before I do that, I wanted to get as high as 16 and as low as -20. So 2, 3, 4, 5, 6. If I just count by ones going up, the highest I can go is 6. If I count by 2, that'd be 12. So I'm going to count by threes. So this is going to be 3, 6, 9, 12, 15, and 18. Okay, so this scale allows me to get up to 16 on the on the y-axis. I can do the same thing, same units going down. So -3, -6, -9, -12, -15, -18, and woo, we just barely made it all the way down to -21. I don't know why I put a 0 in there, but we'll get rid of that. Okay. Now I could use the same units on the x-axis, but that would actually be really inconvenient. I'm kind of tempted to use use each square be a half, so I can kind of stretch my graph out sideways. But I think I won't do that. I'm just going to say this is 1, 2, 3, 4, and -1, -2, -3. Now we know when x is -3, y is just way down there, far off this graph. So I'll just draw a little arrow there at -2, 0. Oh, let me change my pen color so you can see this better. So we've got this little arrow going down there. And when x equals 2, y equals 0, -2, y equals 0. When x equals -1, y equals 16, which would be up here. When x equals 0, y equals 6. When x equals 1, y equals 0. And 2, -20. Should be down here somewhere. And 3, 0. Back up here again. And then 4 is just off the chart, way up there. Okay, so you can kind of see the shape of the graph. It's going to go up here across the x-axis. It's going to go up. Now, I'm not sure where it's going to turn the corner. Is it going to turn the corner before or after? I have a sense it's going to be before there, and then it goes down, and then it's going really sharply down, and I'm actually off to a bad start here. It hits that point, and then it goes up, and there we go. Now, a couple of things to notice. One, remember we said that a graph with x to the 5th power f of x equals x to the 5th power, we expect the graph to go up, down, up, like that, 5 different direction changes. In ours, we only can clearly see 3 direction changes, up, down, up. Now you can see that this isn't really a smooth curve here, and so sometimes the change in direction is just a little crick in the line instead of a full-on turn and going down again. So it could be like this instead of like this. Okay, and that's probably what's going on here somewhere, and we hit the wrong button, sorry about that. We can't tell for sure where the precisely this line is going and what little kind of kink in the line there might be right here without plotting some points. And we could do it with synthetic division. We can do it with a calculator. We could say x equals 1/2, and we could do synthetic division and get a decimal answer and plot that point. And so we could do this, but it's going to be a lot more work than we're expected to do in this class. So this is good enough for us. We can see the general outline of the graph with these points, and I don't want you to go any further than that. Okay, wow, that took a long time. We started off factoring with our goal being what's the list of the factors, and we know there's 5 factors. We use synthetic division, and once we found a factor, that gave us new coefficients to use in continuing synthetic division and finding the rest of the factors. And the big deal here is that you use the quadratic formula at the end when you get down to 3 coefficients left to find the last 2 factors. Okay, that was factoring, but then we use those factors, especially the ones that hit the x-axis, the roots, and along with some further synthetic division back with the original function to find some more points, just filling in the gaps, and to be able to graph the equation. So this is really the 2 sides, the 2 halves of what we're learning in this unit, this first unit. It is finding the factors of a polynomial function and graphing a polynomial function, or polynomial expression, I should have said, finding the factors of a polynomial expression. All right, well, thank you very much for watching. I hope this was helpful. We'll do another recording where we'll do it a little bit quicker. Make sure and watch that one so you get used to this. Have a great day.